Namaste everyone. Hope you are doing well. Yesterday we learned about interference and different possibilities of constructive and destructive interference. Today we will put a light on wave optics. Second part, that is diffraction, the bending of light around the narrow obstacles. Yesterday we saw that all these phenomena, that a thin film of oil on the surface of water, that soap solution bubble, and the thin film coated on the surface of a lens and camera lens and other lenses, all they interfere, they reflect and refract light at different levels, and those lights interfere and produce interference pattern. We have seen that. Now, today we will go to diffraction. Now, when a CD, the writing part of the CD, this is the part where we read and write the CD, and that appears colored when exposed to sunlight. Similarly, the spider web, when it is exposed to sunlight, it appears colored. These are all the effects of diffraction. Diffraction means bending of light around the narrow obstacles. When light passes by the side of the narrow obstacles, it bends, and the bending is not the same for different colors. Different colors bend to different extent. So you see the spectrum also here. But this is not dispersion. This is diffraction, bending of light around narrow obstacles, and the size of this spider web and the edges in the CD are good enough to make the light to undergo bending. So now what is diffraction actually? It is the bending of light around the narrow obstacles. Thereby, light encroaches into the shadow, geometrical shadow. For example, shadow of our hand on the wall will not be very clear. The edges of the shadow will be very blurred. That is because light can enter into the shadow. It is not very sharp. The shadow of an object on another object. The shadow of a moon on the earth, what do you call eclipse? See, moon, the image of the shadow of the moon is not perfectly sphere, and the light is spread here and there. The light is encroaching into the shadow, and that is called diffraction. So diffraction effects can be seen in many places. Okay. Now, so for the formation of diffraction, we need three things. One is obstacle, like spider web, or ups and downs in the surface of a CD, or anything, any obstacle you want, and you need a source of light, and the light coming from the source of light has to bend in different directions, and the screen has to be placed. The way in which source and screen are placed, we have two types of diffractions, that is Fraunhofer diffraction and Fresnel diffraction. What do you mean by Fresnel diffraction? If the source and screen are at finite distances from the obstacle, if you can measure this distance and the rays coming are diverging rays, then it is a Fresnel diffraction. The source and the screen from the obstacle must be at finite distances. What about Fraunhofer diffraction? If the source and screen are at very large distances from the obstacle, in the sense the rays of light coming from the source should be parallel to the obstacle. So that is Fraunhofer. The name itself suggests, if you write Fresnel, only few letters you have to write. F-R-E-S-N-E-L, Fresnel diffraction. Source and screen at finite distances. Fraunhofer, that goes very long. The name itself is very long. The source and screen are at very large distances. So we will see one type of diffraction. So you need a source of light, and of course the rays of light must be made parallel, and this is an obstacle. From the obstacle, the rays of light will be coming parallel, and they fall on the screen. Now, suppose this is the obstacle. So here the obstacle is, from here onwards I will study what is diffraction. This part I am not interested with. Here onwards, after falling on the obstacle, what happens to the rays of light? And if you observe it, then you will find that after falling on the obstacle, the rays of light, some rays of light move forward directly, and they produce bright fringe here. But some rays of light undergo diffraction. What do you mean by diffraction? Bending because of this obstacle, the gap between the two edges. And those bent rays again meet here, and they produce either bright or dark fringe, depending on the condition. How far this ray has to travel compared to this ray. So now, so here on the screen, you could see bright fringe, dark fringe, bright fringe, dark fringe, and continuously like that. Now, suppose diffraction occurs like this. We analyze it by saying that it is a secondary waves, Huygens secondary waves starting from a slit. For example, if this is the slit, from the different parts of the slit, light rays will be coming out. So when light fall on a window, each part of the window is acting like a different source. From the window, secondary waves start. Now let us consider two waves, secondary waves, starting from the top and bottom of the slit or window. Now, a wave coming from here has to travel less in order to reach here, because this distance is shorter compared to this distance. This has to travel longer because this path is very long. Now, how much longer? That makes this one, whether it is a bright fringe or a dark fringe. We are very sure that this should be a bright fringe. Why? Because the wave traveling like this and reaching here, and the wave traveling like this and reaching here, they travel equal distances. So this should be a bright fringe. But whereas this one we can't say. Now, if this path difference, how much is the path difference? If you draw a normal here, then you will get the path difference. How much extra this will travel? That's what we have to see. So if you draw a normal, you will find that now 1 lambda is the extra distance traveled by this wave compared to this wave. By the time they reach here, this from here, if you start, the length of this wave and the length that this wave has traveled, and from here onwards they are equal. This is the extra distance that the lower wave has to travel, and if that distance is 1 lambda, this is a dark fringe. You know that the condition for the formation of dark fringe is a sin theta equal to 1 lambda, n lambda, sorry. A sin theta, A is the width of the slit and theta is the angle of diffraction. Here, how much angle the rays are bent. Now, if you consider one wave traveling from here, another wave traveling from here, this wave traveling at an extra distance lambda, then you can consider another wave at the center of this slit here. And that will also have a path difference of half lambda. Of course, if this wave is traveling extra lambda than this, a wave starting from the middle of the window will travel an extra half lambda. So they have a path difference of half lambda. And if this crest falls on this trough falls on this crest, then intensity will be 0 here. But this will not survive, because the wave traveling from here and here, these waves are superposing with crest on trough. So for there will be a wave here starting from here. For that wave, there will be a wave here that will destroy it, because for each wave starting from the top of the slit, from this half, there is a wave starting from the bottom of the slit which will cancel each other. So here you don't get bright fringe, you get dark fringe. So for that we will consider the path difference formula. So it is like this. If you consider this one, this case now, then so here you will get bright fringe and here may be the dark fringe. What are the conditions for the production of bright and dark fringes? It is like this. So you need not go for all and every explanation. So condition for the formation of bright and dark fringes. A wave starting from here and a wave starting from here have a difference. This wave has to travel lesser distance. This wave has to travel a longer distance. How much longer? This much longer. What is this one? This is A sin theta. A sin theta is equal to n plus half lambda, means it is bright fringe. So if A sin theta is equal to n plus half lambda, that path difference between the wave starting from here and here, that path difference is n plus half lambda, then this will be bright fringe. What is the condition for dark fringe? Condition for dark fringe is A sin theta is equal to n lambda, right? If A sin theta is equal to n lambda, then this will be a bright fringe. The same point will be a bright fringe. What do you mean by n lambda? 1 lambda, 2 lambda, like this. Now this is 2 lambda. Now the crest falls on trough. This is the condition for dark fringe. It is quite opposite to what we have studied in interference. In interference, for the formation of bright fringe, condition is n lambda. Dark fringe n plus half lambda. But here it is quite opposite. So this A is the width of the slit, theta is the angle of diffraction, and n is the order of the fringe. Suppose this is the first fringe, 0th fringe, n equal to 0. Here n equal to 1, first fringe, and next fringe, like that. Okay. So only this formula is enough. Not very important. This you need not. If you have not understood all these theories, you need not worry. You can, if you have time, you can read it later. But formula is very important. Condition for the formation of bright fringe is n plus half lambda here. Otherwise, dark fringe is n lambda. And A is the width of the slit. Theta is the angle of diffraction. How much those rays are bent because of diffraction. Okay. So this is called central bright fringe now. Which is the central bright fringe? From this dark to this dark, from bright to dark, this is central brightest fringe, and it is called central maxima. And later fringes are crowded, they are not as far as the central bright fringe. Okay, condition for minimum is A sin theta equal to n lambda. N stands for 1, 2, 3, 4, 5, etc. Now suppose you stand at the slit. Now slit is made very narrow. If you stand at the slit and try to see this central maximum, brightest fringe. Where is the brightest fringe? It starts from the dark up to this dark. This is the central brightest fringe. What is its angular width? If they ask that question, what is the angular width of the central bright fringe? And we don't work out this problem in the theory. So what is the angular width of the central brightest fringe? Now suppose this is to be asked, then if this theta is to be asked, so you want to find out, say, x. This is the half width of the central fringe. Central brightest part is this one. Central fringe, its brightness goes on decreasing and it becomes minimum here. This is the dark point. This is the half width. This is the full width. So can't you connect this x and this theta? How do you connect it? L equal to r theta. L is the length of the arc, that is x. R is the radius, that is d, capital D, and theta. That's how we can write it. So a sin theta equal to n lambda. We know the condition for the formation of a dark fringe is a sin theta equal to m lambda. Here you may get a doubt. Sir, you are finding the width of the central maximum, that is bright fringe, but you are putting the condition for dark condition, dark fringe. Why, sir? Because the central fringe is spread from the central brightest point up to the dark fringe. So you have to reach up to the dark fringe. When you reach up to the dark fringe, you have to put the condition for dark fringe. You have to reach till you get a dark fringe, first dark fringe, put n equal to 1. Then this becomes a sin theta equal to 1 lambda. But if theta is very small, usually angle of diffraction will be very, very small. And when theta is very small, so can't you put sin theta is almost equal to theta? A theta equal to 1 lambda. What is theta? Lambda by a. So remember that theta is lambda by a. That is the angular width. So angular width of the central maximum, theta, is equal to lambda by a. What about linear width? If you want x, you put x, arc length is equal to L equal to r theta. X equal to r is capital D and theta is theta. X equal to d theta. Arc length is equal to radius into angular position. X equal to d theta. What is x equal to? X equal to, put theta equal to lambda by a, lambda d by a. So what is theta? Angular width. Suppose you look into a tree or a tower which is far away from you. If you draw a line from the top and the bottom of the tower to your eyes, how much angle those two, top and bottom of the tower, will create? That is called angular width. And if you want to find out linear width, convert it into x equal to d theta. So d is lambda by a. So this part is not in the syllabus. So in the sense we don't discuss it in the class, but this is needed. What is the angular width and what is the linear width of the central maximum? So put the condition for the first minimum. First minimum is a sin theta equal to n lambda, n equal to 1, but theta is very small, a theta equal to 1 lambda. That's what you have to do. Then you have to proceed. Okay. Then so a sin theta equal to n lambda. So this is how actually diffraction is seen. This is a laser beam passed through a very small hole. How will be the projection on the screen? You will get a beam here hitting here, less brighter beams. What is this called? Central maxima. That is what is shown graphically here. You see, this is the central brightest region, and here it is brightest. As you go away, the brightness goes on decreasing. Here it becomes perfectly dark. So you see here, the brightness goes on decreasing and it becomes dark on either sides. So this is the diffraction pattern of a red laser beam when it is passed through a small hole. So you can analyze it like this way also. The central brightest fringe, as you go on either sides, the brightness goes on decreasing. Whereas in interference, that problem is not found. All the bright fringes are equally bright and all the dark fringes are equally dark. There we don't have such problem. Okay, this is how we can see that diffraction in day-to-day life. Suppose this is a very large river, maybe the water flowing like this from left to right. But how come it enter into this small lake-like arrangement like here? See, as the waves pass forward, this edge bends these waves in this direction. Can you see the bending here? This is a diffraction seen in water. So bending of water waves, by the time they come across a narrow obstacle, they should have moved forward like this, but they turn like this. Okay. So this is another animation showing diffraction. Parallel beam is incident on a small slit. From the slit, they move as a spherical wavefront like this. Now, suppose you observe two stars on the sky, or a single star. That star may not appear very clearly to you. That may be blurred. That is because of diffraction. So the image appearing in a diffraction may be like this. Now the question is, when you observe two stars like this, if the two stars are far away, you can see them well separated. like this. When they are very close, you feel that they are just separated like this. When they are overlapping, when they are very close, you can't see them separated. So sometimes when you look into the sky, we find that two stars are appearing as a single one. If you closely observe it, at some moment you may find that there are two stars in that point. So this is just resolved, and this is well resolved, and this is unresolved. This is not resolved at all. We feel that there is only a single star, and here there are exactly two stars, well resolved. This is just resolved. So every instrument, maybe a microscope or a telescope, it should have an resolving power. That is ability to show the two closely lying objects as separate objects. It should have that power of discriminating the two objects clearly like this, clearly like this. What is the resolving power of a microscope? 2n sine theta by lambda. You know what are the terms? N is the refractive index of the medium between the object and the objective, and theta is the angle of the cone of rays, lambda is the wavelength of light. Similarly, the reciprocal of this is called limit of resolution, d minimum 1.22 lambda by 2n sine theta. You all these things you know in the theory, you get this formula. So I don't go for the much explanation of this formula. For a telescope, angular, this is the limit of resolution is 1.22 lambda by d. Lambda is the wavelength of light coming from any distant object. Capital D is the diameter of the objective. Telescope will have a large lens that is called objective. Its diameter is d. Resolving power, reciprocal. So resolving power and limit of resolution are the reciprocals of each other. Here also you can see the formula. One is the reciprocal of the other. Here also you know these formulas, and these are the different diffraction effects, and here also you can see them. Okay, then polarization. What do you mean by polarization? Light is an electromagnetic wave. We have seen yesterday, right? Light is an electromagnetic wave. It is a combination of electric and magnetic fields, and they are aligned perpendicular to each other. Now you can see vibrations in all directions in a light. Light contains vibrations in all directions. Now how to confine them to a single plane? For example, if you have a rope, you vibrate the rope like this, vibrate the rope like this, but keep a slit here. Let the rope pass through this. Then only these blue waves will pass through. Here you are vibrating the loop in all the directions, but here only this wave is passing. And now you can see that the wave is polarized here. It is polarized here. The wave is restricted to a single plane. For example, if there is no teacher in the class, every student will be turning back, and another one is moving around, another one is crying, another one is sitting on the desk. That is unpolarized. As soon as the teacher comes, everybody is polarized. Everybody will be looking towards the teacher, sitting strictly in the table. That is exactly polarized light. Similarly here, so this contains vibration in all directions, but by the time it passes the slit, it will contain only one vibration. But this cannot be seen in the case of light, because light is made up of electromagnetic waves and they cannot be seen so easily. So we show it like this. And very important part of this polarization is Brewsters Law. You know this. This part is very important. And one more extra formula you have to add it. What does Brewsters Law say? When a ray of light is incident at the polarizing angle IB, reflected light is completely polarized, but refracted light is partially polarized. You can see that there are few vibrations in the plane perpendicular to this screen, the screen of the mobile or screen of the laptop that you are using. So here the vibrations are all in all the planes. Vibration in the plane of the figure, vibrations perpendicular to the plane of the figure, all the vibrations are found. But reflected light strictly contains only vibrations perpendicular to the screen now. Here this contains, there may be some vibrations like this, and contains most of the vibrations like this. Refracted ray is partially polarized, not completely. This is completely polarized, reflected. This is unpolarized. And now at this moment, when the reflected light is completely polarized, we know that this ray and this ray are at 90 degrees, right? The reflected and refracted rays make an angle of 90 degrees. That is, IB plus R should also be 90 degrees, because totally this should be 180. If this is 90, this should be 90. So IB plus R is 90. That is Brewster's law. At the polarizing angle, the reflected and refracted rays are perpendicular, and the angle of Brewster's angle of incidence and refracted ray, refracted angle, then they're added, you will get 90 degrees. And one more thing you have to know, when ray of light is incident like this, instead of traveling in the same direction, this is not in the theory, when instead of traveling in the same direction, it bends towards the normal. So what is the deviation? This is called deviation. Now if you produce this forward like blue line, then this is IB, this normal and this original direction, then this full angle is IB, right? From the blue line to this black line, angle is IB. Here it is IB, here is also IB. So what is the angle of deviation? What do you mean by deviation? From the original direction, how much the ray is bent, that's all. If this is D, then it's I minus R. This is IB minus R. So angle of deviation is IB minus R. Total 90 degrees is equal to IB plus R. These two equations play an important role. And one more equation, tan IB equal to N. That you know, right? Tangent of the Brewster's angle is equal to refractive index of the medium. That one is however needed. That is Brewster's law. And another is Mons law. That is very important, Mons law. So these two, this one, Mons law, A sin theta equal to L lambda, and Brewster's law. These play a very important role in this diffraction and polarization. Of course, in interference, you have many formulas like condition for constructive, condition for destructive. All of them are important. Then as you solve the problem, you will come to know. But you should know the theory behind the formulas also. Mons law says, right, when an unpolarized light is incident on a polarizer, these vibrations will be present. And when it is passed through another analyzer, another polarizer, now the vibrations are not parallel to this axis. So a part of the vibrations are allowed to pass through. Now what happens is intensity of light decreases. Any polarized light will have lesser intensity because some of the vibrations are cut short. Only vibrations parallel to the axis are allowed to pass through. Now if this intensity is high, any be careful here, just listen carefully. Any unpolarized light, when it is incident on a polarizer, outcoming light will have an intensity half of the incident intensity. Whereas if a polarized light is incident on another polarizer or analyzer, which is having an axis at an angle theta to the incident light, then the outcoming light will have an intensity I is equal to I naught cos square theta. Remember, this formula is applied only for that case when polarized light is incident on an analyzer. I is equal to I naught cos square theta, where I naught is the incident polarized light. This is the outcoming intensity light. So we will analyze this when we go to the problem. But just now, for the time being, you remember the formula. So Mons law is important here. Okay. So if you are sleeping, please wake up. We will go to the problems, right? We will see the problems one by one, and I will display the problems also. You can look into the sheet later. It is already given PDF form, but you can see the problems later. But here it will be displayed. So you can take a sheet of paper and you can write down what are the things needed. Okay, we will go to the problems. Right. Thank you. We will see in the problems. Problems I have put in the videos, and I will write it and show it. Okay. Wait a little.